Okay, so if you recall, in our last class, we started with derivative of a factorial function. Okay, fine. So the derivative of factorial function, say RT, in terms of its component, we had already defined them in terms of your space curves, in terms of space curves. Okay. And then we define that the derivative of the factorial function R, which is denoted by this symbol or this symbol, and it is simply something like as h tends to 0, your R t plus h minus R h divided by h. Okay, fine. So, just one thing I would like to do, I mean, in the books you can get them in terms of a theorem. So basically what this theorem tells you that if R is given by this factorial function, then the derivative of this is simply this way. And this is pretty straightforward. Let me tell you how this happens. Like if I go by this definition, if I go by this definition, so then what is going to happen? Your R prime t, this is simply going to be limit your h tends to 0, f of t plus h minus f of t by h, and so on, isn't it? And from here, you know that this is nothing but the derivative of the function f at the point t. So eventually, I am going to get something like this. So it is pretty straightforward. Okay, so you don't need to worry about it. So what I would like to tell you is that, I mean, whenever you want to find out the derivative of a factorial function given in terms of its components or in terms of a space curve, so then what you have to do, you have to simply find out the derivative of its components and place it there. Okay. Say for example, I have taken the space curve example of the helix cos t sin t. Okay. So for this function, if you want to compute your r prime t, so it is simply derivative of the individual components, that is minus sin t cos t. That's it, is as easy as. Okay, fine. So now what I'm going to do, I'm going to show you some results. Okay, I'm going to show you some results. So this is about that theorem that just I have told you. Okay. And of course, here you have to remember that the individual component functions, they have to be differential functions. Okay. So in that, then these happen. So next thing is that these are, I mean, although this is they are, I mean, depicting them as theorems, but these are simply results. These are simply results. So what I like to do, so I simply do one of them. I simply do maybe. Let me do 5. Let me do 5. I'll simply do one of them, and then the rest you can try it on yourself, and you will see that it's very straightforward. And making use of this property 4, I'm going to derive something which is going to be very useful later on. Okay, fine. So that is what I'm going to do. So let me try just one of them. It is just mathematical manipulation. Let me check how it happens. So the theorem 5, I think it was this derivative of so this is your Okay, fine. So now, if I want to do the proof, say this one, ddt of this. So this is equal to what? If you go by definition, this is simply your limit h tends to 0. Then u t plus h v t plus h minus u t plus v, and of course divided by h. Okay. So now we are going to do the manipulation here. We are going to do the manipulation here. So what we are going to do? This one, this is fine. U t plus h cross u t plus h. But what we are going to do? We are going to introduce a term here. That term we are going to do u t plus h cross your Vt, and we are going to again, since I have to neutralize this, I am going to again t plus h Vt and then minus Ut plus V. Okay, this is what we are going to do. Fine, and then I mean, you know, the rest is going to be pretty simple. Then from the properties of cross product, and if we bring the limit inside, what I can do, this eventually I can write as limit h tends to 0, your u h tends to 0, this v plus h minus vt divided by h, and then this one I can write as limit h tends to 0, ut plus h minus ut this cross vt. In fact, I could have written one more line there, but I hope you will understand, right? Is it okay? Right?
Yes.
So thank you. So now you know that this is simply ut, and by the definition of derivative or a back-funded function, this is nothing but the derivative of v. Then again, just a minute, I made a mistake here. So this should be plus. This should be plus. This is plus. Okay. So then again, by the definition of derivative, this is nothing but e prime t, and then that is v. Okay. So just adopt this methodology, and you'll be able to work out the remaining theorems as well. Okay. Fine. Now we are going to use one property later on. So let me walk out with that. I think likewise, that theorem 4, I think that told you that ddt of u dot v. So this is simply u prime v plus u v prime u v. Okay. So now I can get a corollary out of it, or I can manufacture a problem from this. What is that? Say, suppose I manufacture a problem. If say u is a vector of constant length, then u and u prime are orthogonal. Okay, fine. So the answer will be something like this. See, by the given property, I have been giving that This vector u has constant length. If I assume that length is say a, so that means I am going to get mod of u equal to a, and where this a is constant. A is constant, right? So this implies.
Sir,
Yes.
it will be v prime, not u prime, I think. Orthogonal.
No. I'll come to that. Don't worry. You will see that it will come out. U and u prime are orthogonal. If u is a constant vector, I mean, if u is a vector of constant length.
Okay.
Okay, I'll prove that. Okay, so then u square equal to a square. Okay, so this implies u square is nothing but u dot q. This is a square. So now, if I take derivative, so ddt of u dot u equal to 0, isn't it? Because derivative of the constant function is 0. So now, if I use this result, so this is going to give me your u dot u prime plus u prime dot u. This is equal to 0, right? Okay. So now,
Yes, sir.
now you you know that your vector dot product, it is commutative, isn't it? A dot b is equal to b dot a. So from these two, I am simply going to get like 2 u dot u prime equal to 0, and this implies u prime u dot u prime equal to 0. So that means u and u prime must be perpendicular to each other. Okay. So next slide. Equal to 0. So this implies u prime is orthogonal to this. That's okay. This result we will need later on. So that's why I'm doing it right now. Okay. So this is about your differentiation. Okay. So now let me have a quick look at integration. So math for integration. Okay. And again, here, just let me tell you. See, whenever we talk about, I mean, differentiation of a vector value function, you must remember that its individual components, they must be differentiable themselves. Only then I'll be able to get the derivative of the original vector value function in terms of f prime, g prime, and h prime. Okay. So now let us again consider a vector value function so given by ft, gt, and ht. Okay. So if you recall what we did, like say whenever we consider a function, say this is t, and suppose this is f of t. Okay, fine. So if we consider the integration of I mean this function from the point A to B, fine. So what we did, we basically divided into some what AB into subinterval, and then what we did is we considered these areas, right? We added them, and as the number of these sub-rectangles increased, if we tend to infinity, so then the limit of that sum, limit of the sum of all the areas of this some rectangles, it was giving me this integral. Okay. So similarly, if I consider this R to be a vectorial function defined in the interval AB, so like there is a theorem. I mean, sorry, it's RT dt. This is simply this A to B FT dt, A to B ZT and A to B XT dt. Okay, fine. And again, here also you can apply a fundamental theorem of integral calculus, fundamental theorem of integral calculus. So what is that? Integral calculus. So remember, there is not necessarily only one fundamental theorem. There are several. So, but this one I think you should be familiar with. I'm not going to spend much time on this. Say, suppose this vectorial function RT such that it is the derivative of another function R prime t. So that means what?
Capital RT is the antiderivative.
Antiderivative. Yes, capital RT is the antiderivative of small r, right? So then your A to B small r RT dt. So this is simply R B minus R. Okay, that's okay, fine. So as before, I mean if you have to integrate a vectorial function between two limits, what you have to do? You have to simply integrate their respective components. That's it. Okay. So I won't spend much time on this because later on, I mean, when I'm going to consider your arc length, etc., we are going to make use of a lot this integral. I mean, those formulas or many exercises which I have accomplished here. It is going to be part of those examples as well. Okay. So and since we will be given a lot of exercises in your tutorial, so I'm not much worried about that. So let us have a quick look at this. So this is about the definite integral of a continuous vector function RT can be defined in much the same way as for real function, except that here the integral is a vector. So this is what I told you, and this is about your picture of integral calculus. Okay, fine. So now what we are going to do, I am going to go into this one, arc length. I'm going to go into arc length and curvature, and this is going to be very, very important. Arc length and curvature. Okay, so just let us start, and after that, what I'm going to do, I'm going to again take you back to those slides so that I haven't missed anything. Okay, so for your convenience, I guess you have already done it in MA 101. So what I would like to do, I would like to give you a quick glimpse of how you try to find out arc length in Cartesian coordinates. Okay, so for that, what I'm going to do. Okay, so what we are going to do now, we are already into the arc length. So what we are going to do now, so suppose I consider a curve C in space in two-dimensional plane, not space. So then, if I consider C to be a graph of a function of one variable, that is like y equal to yx, and I define it in the interval. A, B, right? So then what I can do, assuming that say A equal to x naught, B equal to x on, xn by introducing the points x1, x2, x3, etc. here. So then I'm dividing AB into sub-intervals, and again this x1, x2, x3, etc. They don't necessarily have to be equally spaced. Okay, so it is going to be something like that. And suppose I consider an interval, this interval, your xi minus 1 xi here. I have some special purpose why I have written it like that. So then what we can do, and again remember, we have taken them in such a way that this inequality is held. Okay, so now what we are going to do, we are going to join these points, like this. Okay, maybe I can introduce something more here. Okay, so then what we can do, we can approximate the length of the curve C. So suppose I call it L, and if I call these points, as P0, P1, P2, etc., and suppose this is Pi minus 1, this is Pi, this is Pi. So then what is going to happen? This length of the curve C is going to be nothing but isn't it? Right? What we are doing here, we are taking the sum of all the length of these points lying on this curve, right? And you know that as we let n tends to infinity, that means as we increase the number of sub-intervals being introduced to this bigger interval AB, so then what is going to happen? This is going to define the length of this curve. Is it okay? Fine. So now let us concentrate here. So, maybe what I can do, maybe just let me do it in such a way that it is easier for you to visualize it. Okay, let us do it like this. Okay, okay, fine. So now, what we are going to do, say this is Pi minus 1, this is Pi second. So what I'm going to do, I'm going to call this distance, that is nothing but the length of the interval xi minus 1 comma xi plus denoted by this, and this distance, let me call it as delta yi. Okay, so then you know that this is nothing but your isn't it? So basically what is happening, so let me just magnify this a little bit. So my situation is something like this. So this is Pi minus 1 Pi. Okay, so this is my sub-interval xi minus 1 xi. Okay, so this is delta xi, and this length is delta y. Is it okay? Fine. So then what is going to happen? Your see delta yi. So this is nothing but y at xi minus y at xi minus 1. Isn't it? Because you know that this length is y at xi minus 1, and this length is y at xi. Okay? And Now look at this. Y is a function of the single variable x. Okay. So now if I use what Mendel theorem here, so then what I am going to get, this is going to be equal to your xi minus 1, then y prime xi star, where xi star it strictly lies in the open interval. Is it okay? Fine. And you can see that this is nothing but your delta xi. This is nothing but delta xi, and then y prime xi. Fine. Okay. So now if I substitute it here, eventually, this is going to lead me to 1 plus your y prime xi star whole square delta xi. Okay, and you know from integral calculus, that I mean this sum is nothing but your okay, fine. So now let us come to another interpretation of this arc length. Okay, so basically I'm computing the length of this curve here. Okay, fine. So now let us do it in some other way. Okay, so see, eventually my aim is to reach the length of a curve in space. Okay, so okay, let me still keep this figure like this. Okay, so now let us consider a curve like this in two-dimensional plane. But what I'm going to do intentionally, I'm going to draw this curve. I mean, in some kind of twisted way. I'm going to draw this curve in some kind of twisted way here. Okay, so this is x, 0, y, and again this has been defined in the interval. Say AB, but there's a twist here now. What I am doing, I am defining the curve in terms of the parameter t. Okay, so basically what I am doing, say suppose if you consider any point p here, say whose coordinates are xy, so then if I join P with the origin OP and I get a vector OP, and suppose OP is R, and what I'm going to do, I'm going to define this R as xt yt. So basically R is a function of t here. Is it okay? Fine. So now I mean I have roped in a new variable t, that is nothing but the parameter here, through which I have parametrized the curve c. So basically what I am doing, so suppose I am considering an interval alpha beta in real line, okay, and what I am doing, I am defining two functions, one is x and one is y, from the interval alpha beta to the set of real numbers, okay, in such a way that what is happening out here. So what I am doing here, so my a here is nothing but x of it x of alpha? No, right? It doesn't have any relation with A. It has relation with what? It has relation with what? No. So what is going to happen? Like if you consider this point and this point, if you consider this point and this point, so that means what is going to happen? Your of course your A is going to be x alpha and y of A is going to be what? Y alpha. Isn't it? So similarly here, your B is going to be x beta, and your y of B is going to be y beta. So basically, what I'm doing here, I am for t belonging to say alpha beta, t belonging to alpha beta. So what I have defined here, okay. I am defining a function. From the interval alpha beta. Okay. Say suppose this interval alpha beta is something like this, and from here I am defining two functions, your x and y. Okay, so then here the corresponding points are xt and yt, and I am assuming that these functions x and y, they are continuous functions. Is it okay? Fine. So now through this I have parameterized this curve p of xy. Is it p of xy? No. I have parameterized the curve C. Okay, so maybe I can give some direction here, so that it is the curve which is being drawn from this point to this point. Okay, fine. So basically by this, what I have done. See, this vector is simply R alpha, and this vector is simply R B. Is it okay? Fine. So now another thing, just look at these two graphs. Okay. Should I use the word graph here? I have given you some hint. Okay. So now look at this curve. Look at this curve which we drew here. I'm calling it C. In the xy plane, when I drew this curve, in such a way that this is nothing but the graph of a function of one variable. This. Okay? So now I have intentionally drawn this curve in xy plane in such a way that what? This is not the graph of a function of one variable, because you know that the way I have drawn here, if you draw a vertical line here, it is going to cut the graph at 2 points, right? Isn't it? Right? So it cannot be the graph of a function of one variable. But what I have done here, because I have parameterized it, despite this being not the graph of a function of a single variable, still we can find the length of the curve in some other way. Okay? So what is that way? Let us come to that. Okay, fine. So what I'm going to do here now, okay, the interval alpha beta, on which your t lies, so what I'm going to do, I'm going to divide it into, and again sub sub-intervals, again, like say 2D points, say alpha equal to T1 and beta equal to say Tn, and then T1, T2, etc. Then say this is the point Ti minus 1, this is Ti, this is Ti, and then what I'm going to do through these points, they are going to define some corresponding points lying on this curve, isn't it? For example, say consider this one. Okay, so then what I'm going to get, I'm going to have a pair like xti y this and a pair like xti y ti, right? So basically it is going to give me say 2 points here, pi minus 1 pi, right? Whose corresponding coordinates are given by this. Is it okay with everybody? Right? So what I am going to do, as before, what we are going to do, we are going to have points like P0, P1 up to Pn lying on this curve, okay? Go. So we have points, I mean, you can see here, when we consider this curve C as a graphing function, we have points P0, P1 up to Pn lying on the curve. So similarly, this curve, which has been parameterized through the variable your t, we can also have points like them, like P0, P1, Pi minus 1, Pi, Pn, okay? And again, if I consider these points, 2 points Pi minus 1 and Pi, again, corresponding to that, I will have an interval, Ti minus 1 comma Ti, and which lies in the bigger interval, alpha beta. Is it okay? Fine. So now, as before, what we can do, we can simply join them, all these points by straight lines, like, okay, and then eventually what is going to happen, as before, now your as before, the length of the curve, so this is simply going to be limit and tends to infinity, and again sum of this. Okay, now you can see that what is happening out here. Again, what we will have as before, we have delta xi and delta yi. Okay, we will have delta xi and delta yi. So now your delta xi, so this is simply xi minus xi minus 1, and again you know that xi is nothing but x this, and xi minus 1 is x this. And again, if we use mean value theorem, so then from here, what I'm going to get, to be precise, so this is equal to this, and then something like Ti star, x prime Ti star, where your Ti star lies in the interval, the second interval. Is it okay? Right? Because we have already assumed that your x and y, they are continuous functions in the interval alpha beta, right? Defined from alpha beta to the set of real numbers. Okay. So now, similarly, what we are going to get? So for delta yi also, I am going to get it like something like this, delta ti, and then y prime, and then maybe I can write it as ti double star, and of course ti comma ti double star, they lie in this sector. Is it okay? Fine. So then what is going to happen? Then what is going to happen? So what I am going to get? I am going to get L equal to eventually and tending to infinity, say this. So this is going to be equal to limit n tending to infinity, and then square root delta xi squared plus this is in fact n tends to infinity summation of going from 1 to n. Okay, and eventually what I'm going to get, if I substitute these two, and of course if you see ti minus ti minus ti minus 1, I have already written it here, so I can simply write it as delta ti and this x I prime ti star. Okay, so if I substitute these two, here, this one and this one here in this expression, what I'm going to get? So this is going to give me limit n tending to infinity I equal to 1 to n, and from here eventually I am going to get y I prime I double star whole square, and then this is going to be delta ti. This is going to be delta ti, and you know that from definition this is nothing but dx dt squared plus dy dt squared dt, and what about the limits? What about the limits now? A to b. It is alpha to beta. It is alpha to beta. Is it okay? Fine. So in this way we can find out the length of a curve in two-dimensional plane where the curve has been parametrized through the variable t. So likewise, now say suppose you have a curve in three-dimensional space. You already have an idea how we have evaluated the length of the curve in two-dimensional plane. So if it is three-dimensional space, say this is x, y, j. Okay. So then if you have a curve like this in space, so again what I'm going to do, say a general point here, so P R. So this is now what it is going to be. It is going to be something like xt, yt, jt, right? So now I have three functions. X, y, and j defined in the interval alpha beta. Okay, from alpha beta to the set of real numbers. Okay, and then as before, what is going to happen? Like say this point, this is going to be r alpha, and this point it is going to be r beta. Isn't it? The position factor of those points, right? And apply the same methodology. Okay. And then, if you apply the same methodology, what you are going to get? Eventually, you are going to get the length of this curve, C simply as alpha to beta, dx dt whole square plus dy dt whole square plus dz dt whole square, then dt. Is it okay? Fine. So I'll next show you the slides. in Cartesian coordinate system. So you can see here they are simply taking out this length and they are highlighting it. And what they are doing, they are successively, I mean, they are letting n tending to infinity. So that is going to increase the number of subintervals and number of this polygon size. Okay, fine. And this is what it is. And this was the arc length formula. Because I have already said continuous differentiation. So they say that f prime is continuous on the right? So then the length of the curve y equal to fs in this interval is given like this. Okay. And again, the same methodology. I mean, if we apply, and I have already told you what is the distinctive feature of considering a curving plane in terms of the vectorial function, and again a curve as a graph or a function of a single variable. Okay, so this is the way we can decompose this curve. Okay, and eventually, if a curve C is described by the parametric equations x equal to ft, y equal to gt, where t lies between alpha and beta, and of course this f and g are continuous differential function on alpha beta, and this is t c is traversed exactly once as t increases from alpha to beta. See, this is important. T increases from alpha to beta. See, whenever I am going to consider this space curve or plane curve in terms of a vectorial function, I should always consider the original interval of the parameter t in such a way that it is indeed increasing. Okay, so that we are able to track the curve. That is going to be very, very important. Okay, so this is about I mean in 3D. This is about the length of a curve in 3D. Okay, so then what we are going to do. And this is very obvious, right? This is very obvious. So I'll come back to that again. So now parametrization of a curve with respect to the arc length. So let us concentrate there. Yeah. So this length, if your R is given by xt, yt, jt, so then you know that your R prime is simply x prime t, y prime t, j prime t, right? From there, you can see that the expression under radical sign, it is nothing but the magnitude of the derivative of r, isn't it? Right? So that is why this can also be written as this. Okay, fine. So now let us come to that parametrization part. Just a minute. Okay. In fact, we have already done. I mean, like say, expressing the curve in terms of this, in terms of this itself is a parameterization. So I have parameterized the curve in terms of the parameter t. Now the thing is that this parameterization is not unique. Instead of t, you can use some other variable also in order to parameterize the curve, and eventually both the parameterization or whatever number of parameterization you use, if it is accurate, so then all of them are going to give you the same length of the curve. Okay, so for example, say suppose I am considering a curve C. I'm considering a curve C, which is parametrized, by say this T square T. Okay, and T goes from 1 to 2 in this interval I'm considering. Okay, so now I may define your T to be equal to some e power U, right? So then what is going to happen? I can re-parametrize this. Say suppose this was something like R1, and I can re-parametrize the same curve with another function R2U, right? 5. So T is going to be e to the power U, e to the power 2U, e to the power 3U, right? And then your U is going to go from what? Now U is going to go from
0
up to. Okay, fine.
Yes.
So yeah. So now you may be thinking why basically, although I am saying that parameterization of a curve, but basically I am talking about re-parametrization of a curve. Okay, I can re-parametrize. Okay, so you may be thinking why it is important. I'm coming to that. Just a minute, let me just shake off the dust. Okay. Now I come to the arc length function. Arc length function. Okay. So let's consider, say, this curve in space. This curve in space, and I'm say suppose considering this curve to be simply your xt, yt, zt, and let us assume that t belongs to the interval say u. Okay, so then obviously your this is the fixed curve R A. This is the fixed curve R A. So see earlier we were considering the length of the whole curve C. Suppose I would like to consider only a part of this curve. Say suppose I consider only an arc. I consider only an arc. Okay, I consider only up to this. Okay, right? So I can think about only up to this point. I can think about only up to this point, and so on. Isn't it? So if I take a variable point t belong to A, say suppose I consider another curve RT here. Okay, and I simply want to find out the length of the curve traced out by this vector. Trace out by the vector moving from this point A to this point T, right? So earlier what our formula was? Our formula was the whole length was simply your A to B, your R prime T, dt, isn't it? Fine? But now, if I want to find out the length of this R only up to a certain point, then this limit is going to go to a variable point. Is it okay?
Yes.
Yes, sir.
Yes. So then because this variable point I am considering it as t, I cannot use t as my variable here. I have to use another dummy variable, right? So that dummy variable, let me call it, maybe you can call it u as whatever it is, don't worry about it, okay? And then this is going to be t2, right? And this arc length is going to depend upon the value of this t, isn't it? So it is going to be a function of t, right? So this expression, which gives you the length of this arc from the initial point A to a variable point t here, to a variable point t, that is called the arc length function. Okay, and this is in fact this st is this blue length of this blue curve. Are you getting my point? Right? This is st is nothing but the length of the blue curve. Okay, fine. So this is nothing but the arc length. Okay, so now this re-parametrization thing that I did, that is going to come in handy. Okay, so yeah, from here there can be another direction. Then I will come back to this re-parametrization of a curve. So here, one result from this is that if I use fundamental theorem of integral calculus, as I have told you, there are a few fundamental theorems of integral calculus. So now, if I find out the derivative of this function with respect to t, that is, if I try to find out ds dt, that is going to be what?
Mod
Yes.
t.
Yes, that's it.
Minus. No minus.
No minus. Simply mod this one. Simply this integral. Simply this integral with the upper limit. That's it. Okay, fine. So this result also we are going to make use of later on. So now let me come to the re-parametrization of a curve. So, and again, whenever we talk about arc length or re-parametrization, in the exercises or in the book, always they are going to tell you about in the increasing direction of t. In the increasing direction of t. You should remember that. Okay, so now, just now from this expression, from the definition of the arc length function, you can see that this is going to give you. So this s, you are going to get it is a function of t, isn't it? So that means sometimes, I'm not saying that always you should be able to explain. So sometimes you should be able to express t explicitly in terms of s. Is it okay? Fine?
Yes.
So that is going to give you a way of re-parametrizing a curve. So let us take one example. Say, suppose I want to re-parametrize the curve, nothing but the ellipse, this one, in terms of cos t, sin t, t, okay. So if I want to re-parameterize this in terms of the arc length function, let us see what happens. Okay. So now from the definition of the arc length function, I will be in r prime. So that is why firstly, let me just calculate it. First, this is 1, right? So your mod of r prime t, this is simply going to be root 2, right?
Yes.
It is simply going to be root 2. sin square t plus cos square t plus 1. So root 2. Right? So now, if I use this formula, this is going to give me S equal to, say, suppose I am considering this interval from 0 to some increasing direction of t. Increasing direction of t. Okay. So then 0 to t, then square root 2 d, right? Square root 2 d. So this is simply going to give you, square root 2d. Is it okay? Fine?
Yes.
So that is giving me an idea that what I can do. So that is t equal to s by square root 2. Square root 2. So now let me tell you, if you were defining the curve, say suppose from 0 to 2 pi, from 0 to 2 pi. So then I am going to re-parametrize this. So RT equal to simply R T as a function of S, right? So this is going to give me cos S by square root 2 sin S by square root 2 and this is T S by square root 2, and the interval is going to be 0 to 2 by 2 to 2 pi. 0 to interval is going to be here 0 to 2 root 2 pi. Fine. Okay. So that means, like say this one. The arc length function, it provides you a way with, re-parametrization. Okay, so it gives you a way to re-parametrize the re-parametrize a curve. Okay, so if you are seeking another variable, arc length function is going to give you that variable. So let me see whether I have missed anything or not. Just a minute. This I have already explained. Yes, and this is a finite form. This is a finite form. Okay, so maybe this curvature and curvature and what? Yeah. So curvature, then your normal, binormal, all this stuff. I'm going to do it in my next class. Okay. So then let me stop here. Let me stop here, and then I will see you in my next class then.